So we'll start this section with ecology and the biosphere. And what we want to do is talk about what affects where things live. And so if you look here, they're kind of dividing terrestrial versus aquatic, which we will do late in one of the later videos. But we want to first start talking about some of the factors that affect where things live. And so here, what we're seeing on the left, the terrestrial organisms where they live are extremely affected by temperature and precipitation. And you see the climate. I want to make sure that we have a distinction between weather and climate. Weather is that day-to-day thing we have. So what is the temperature today? What is the rainfall today? Climate is more kind of a long period look at what it is. So for Walnut, California, the average temperature is probably in the upper 70s. We're a Mediterranean climate, so we have hot, dry summers and colder, wet winters. And our rainfall is on average about 12 to 14 inches. So those are the things that we be looking at for terrestrial organisms, whereas with aquatic organisms, a couple of different factors. One is light, because we need photosynthesis. We need a way to drive that food web. And then other is nutrient availability. So what you're going to see is, which we do see, is more aquatic life kind of along the shores where you're getting shallow areas which are getting a lot of sunlight, so photosynthesis can occur, and also nutrients are washing off the terrestrial areas that are allowing things to grow. But there are other areas that are also very productive that aren't necessarily right there on the shoreline. So that's what we want to talk about on this one. So to do that, what we really need to do is look at kind of global climate patterns. We're not going to go into this in too much detail, but if you look here, you can see that the light does not actually hit the planet equally at all times. We are a globe, an orb. And so what happens is not every terrestrial area or aquatic area for that matter gets the same amount of sunlight all year long. And so you can see here that sunlight directly over the equator is pretty straightforward, whereas as you go toward the poles, what you're seeing is a lower angle. And then again, the Earth actually rotates on its axis and shifts. So that will change during different parts of the year. So what we want to do here is look at that tilt. We have this kind of 23.5 constant tilt, but it depends on whether the Earth is tilting toward, or at least our hemisphere is pointing toward or away from the sun. And so what I would like you to know is there are two solstices, and that's where we're tilting at our, kind of at the most toward the sun, is the June solstice. And that'll get you, the longest day of the year is June 21st. And then the December solstice is where North America and the Northern Hemisphere actually is tilting away. And that would be our shortest day of the year, December 21st. And then when the equator faces sun directly, those are called our equinoxes. We have one in March and then another one in September. And those are when the days and nights are pretty much equal. So this tilting back and forth is setting up global climate patterns, depending on how much sunlight is happening at what part. The other thing I want you to know is solar radiation at the equator kind of drives these precipitation systems. The air circulation will do that. And so what I want you to realize is we have these what's called convection cells. These are what these things are called. They've got all kinds of different names, and each one of these is named differently, which we're not going to learn. The one here, I believe, is called the Hadley cell. But what happens is at the equator, is it's warmer and warm air rises. Also, it has a lot of moisture in the air, so moisture goes up. As it heats up, it goes up into the atmosphere. Now, what happens is as it gets higher, it gets cooler. And as the air cools off, it can't hold as much water, and then that water dumps back down. And that's why the rainforest is the rainforest. It's getting a lot of rain. Now, what I do want you to understand, though, is that cell, that convection cell, actually sets up the cell next to it. And you can see how these cells are working. So things that are happening in the tropical areas are actually setting up this cell here, which then would set up the cell up by the polar ice caps. And that is important because when we get changes in our tropical rainforest cells, that will affect global weather patterns. And we're starting to actually see that with climate change, which we'll talk about a little bit more. Also, wind patterns make a big difference. So here you can see the kind of the wind patterns that happen around the world. And you can see there's areas called the westerlies, and early on shipping, when it was all sailing ships, they had to be very careful on how they did things. They wouldn't sail just directly back and forth. They kind of would follow what we call these gyres that happen. And so what we would see then is the westerlies was one of those routes they would take, because the winds are in the southeast trade winds, again, you could see, because and the northeast trade winds would be used to push the sails. Now we have things right here called the doldrums, which means that there could be periods of time where there is no wind, and that could be very dangerous for a sailing ship that got caught in this. And what they're not showing you is another name here, right there at 30 and 30. Those are called the horse latitudes, and they call them that because if a ship got caught in those and for long periods of time and they weren't moving, they would actually throw the horses overboard because they couldn't feed them. Yeah. So anyway, these setup patterns, and again, I want you to understand, when we look at climate, we look at all kinds of things: temperature, water, light, wind. All of these become important conditions as we try to set up what kind of plants and animals and things are going to be in a given area. There are also local effects. You hear a lot now about microclimates, and these are specialized areas. Now, one local effect is mountain ranges. Now we have this north-south mountain ranges here in California, and so we have what's called the rain shadow effect. And so our storms typically come off of the Pacific Ocean, and the winds blow, and so what happens is all the clouds and the moisture gets up and over the land. It'll drop. Now, what usually typically will happen, though, is there is the mountain range. If you drive down the 10, you're actually kind of driving through the middle of it there. And what will happen is the clouds will bump into, not actually physically bump into, but bump into the mountain range, and the air rises. As that air rises, again, it gets colder, and any moisture in those clouds will dump on the one side of the mountain range. Now, when it gets up and over those clouds, then will dump back down. It's warmer. They've already lost most of the moisture, so that's why we have where our local deserts are on the other side of those mountain ranges. Most of the wind drops, or most of the rain drops on this side. Often our deserts get some summer storms, and that is actually not coming off the Pacific Ocean typically, but that is coming down from the Gulf. So they'll get some hot, humid days sometimes, and that's usually storms down from Texas and the Gulf area that get blown up. And we may not see that in the valleys where the desert might get a little bit of rain. All right, and then these are the gyres I was talking about. The wind patterns will form these ocean gyres. And you can see, again, these big circles of water moving. And so I guess what I want you to know for this is you probably should know that the California current is the one off our coast, and it is a colder set of water coming down from the north that runs along, and then we get disruptions in this, and you might have heard of El Nino and El Nina, where we're actually getting warm water from down here coming up, and it kind of disrupts this current. And so then we end up with either extra rain or less rain, or who the hell knows, but yeah, it changes quite a bit. So yeah, so these ocean gyres set up things. And here's a concept I want to talk about with the tropical rainforest and even our area. Cities do not do well when it comes to rainfall and things. What will happen is you cut down forests or greenery, all those plants are transpiring. They're losing water through the stomata we talked about. And so if you now don't have that to catch it, those transpiration rates slow down. And so what we find is deforested land surfaces tend to have higher temperatures. Unfortunately, even more so if you don't leave it as dirt and even small plants, what you then end up with is even warmer, because cities have things like sidewalk and asphalt and metals, and that tends to absorb heat. So definitely huge changes, and we're seeing that today with the tropical rainforest being cut down. That is changing some of our weather patterns. And climate change, just kind of mentioned it here. We've been in a pretty steady range of climate, and we've had ice ages and we've had warming up trends, and that's all true. But those have always been within kind of a range and a pattern. What we're seeing over the last couple hundred years is temperatures have risen because of urban growth. Some of the things we've talked about already. And what the problem is we're talking about a major, change of, again, 2 to 3 degrees. But what we're worried about, especially, is this rapid change in temperature, because evolution, for the most part, is fairly slow. And what's going to happen is we're going to see major changes. Some species aren't going to survive. So here's just an example. It was in your book. It's an American beech. It's a type of tree. We don't really have a lot of beeches out. We have beeches, but not beech trees out here, spelled B-E-E-C-H. But the American beech is found on the east coast of the United States. And this is what is expected to happen to them if global climate change gets to kind of the extreme temperatures we're talking about, at 6.5 degrees change. The 4.5 is unfortunately kind of what we're predicting might happen if we don't get our act together. 6.5 would be catastrophic. Here all we're doing is seeing the plant shift from their range, and that's assuming it's slow enough and they can move. But we're having things like polar bears, which are having trouble feeding because of the ice flows melting and less seals, and unable to capture seals, and all kinds of different reasons. And we're actually seeing changes where you're seeing brown bears and polar bears actually breeding. We're coming up with these hybrids to trying to survive. So definitely some major changes. And we'll stop the recording there.